will be Martin Zwierlein, who has now announced his title of his talk.
Yes.
Thanks.
So yeah, actually, thanks for having me. To the other organizer, I thought I would not even speak. Then they asked me to maybe give some talk about some techniques and stuff. So I didn't provide a title, but that was good because I could now quickly change the title to this one, quantum transport in strongly reacting Fermi gases. I will talk about sound modes, and these are actually sound modes that we observe in our box potential. And I stole part of the talk from Richard, who will give a talk about some brand new TBD subject. Tomorrow, it'll be declared tomorrow what the title will be. It's going to be awesome. You should show up. Thanks, Richard. I should be in the presentation, right? I should try to be. Does it work? Perfect. Okay. Yeah. So just to set us on the scale here of things. Of course, strongly interacting Fermi systems are all over the place. In terms of the length scales, we find them, of course, in nuclei and in neutron stars, white dwarfs, and of course on the human scale. For example, I showed high TCs. I should have probably shown also some cool vortex tangle in helium-3. Those are generally systems that are difficult to probe in situ, microscopically take pictures of them. And so the cold gases are very nice way of actually getting a direct view at these strongly interacting Fermi systems, taking pictures of vortex lattices, for example, and studying the microscopics. So, of course, there are many topics that are connected between the strongly interacting Fermi gases. I picked here this beautiful paper by Aurel and colleagues on understanding nuclear fission. That's a strongly interacting Fermi system. Here, these nuclei that are very difficult to model, even though they managed. Strongly interacting Fermi gases in our ultra-cold setting can also hopefully be a way to check whether certain theoretical approaches in dynamics are working. Of course, now we have measurements on neutron star mergers from LIGO, wonderful. They don't quite have pictures like these, but they have good artists making these beautiful pictures. In high TCs, of course, all of condensed matter is full of complicated questions. And as we have seen, of course, in helium-3 also, of how does transport even come about? And there are many things we don't understand. In high TCs, one example is the strange metal phase, by the name of which you already know we don't understand much about it. Otherwise, we would call it differently, I guess. And I will have something to say about such a strange metal connected to the fact that also in our systems, they are not well-defined quasiparticles that would simplify the description. We also have a soup of strongly interacting atoms that behave in strange ways sometimes. The setting will be lithium-6, my favorite atom, at one of these Feshbach resonances. So if you haven't heard about it, I have to tell you, these are wonderful tools with which we can tune the interactions between our atoms, the lithium-6 atoms. And that tool comes about because you can take two free atoms, let's say a red and the blue ball, and usually when they come together, they find some interatomic potential that gives them some phase shift, and then they leave again, and nothing very special has happened. However, if there is a molecular state nearby in energy in this interatomic potential, you know that the scattering phase shift will be large. Now, if you can tune such a molecular state into resonance freely, then you can actually tune the interactions to be resonant. And this knob we actually have in our hands in the lab. It's the magnetic field that we apply onto our lithium-6 cloud. So we can tune freely from a weakly interacting Fermi gas to a strongly interacting Fermi gas just by applying an overall magnetic field. And that is wonderful, and it gives us this ability to explore physics where the scattering length has gone through the roof and you're left with a unitarity limited phase shift of pi over 2, right on resonance. This actually, in the many-body world, gives rise to a beautiful crossover between a Bose-Einstein condensate of tightly bound molecules, when you have tuned the interactions such that they all form now these small molecules, to a Bardeen-Cooper-Schrieffer state of long-range Cooper pairs, going through what we call a crossover superfluid, where the pair size is on the order of the interparticle spacing. The fact that these gases are even stable at the Feshbach resonance was actually shown by Christophe over there, who demonstrated for the first time that these molecules actually don't collapse when you bring them near this Feshbach resonance, but it's a wonderfully healthy system that enabled the entire research in the field afterwards. So this unitary Fermi gas is a special point that we love because it's a scale invariant point of the system. Unitary means I tune my Feshbach resonances right, right to the resonant point, and now the scattering length has gone through the roof, it's infinity, it has diverged, and I'm left with only two length scales, the interparticle spacing and the de Broglie wavelengths, corresponding to the two energy scales given by the Fermi energy and the temperature. So the interesting point is on this axis here, right at 0 inverse scattering length, and the strongly interacting regime is anywhere where the interparticle spacing, characterized by the inverse Fermi wave vector, is on the order of the scattering length or smaller. So that's this interesting strongly interacting regime. And the equation of state is universal at this point, in the sense that it can only depend on the energy and temperature. And it even simplifies further as you go to 0 temperature. There, the energy of the system can only be some universal number times the interaction, times the ground state energy of a non-interacting Fermi gas. There's simply no other energy scale available at 0 temperature. That number we measured to be 37%, and other groups also measured. Yeah?
Did you lower the precision? I had the impression you know the third digit was better precision.
Well, I did round it, given that our error bar is what it is. So it's a...
Smaller than that. Your error bar is smaller than that.
No.
It's half, about half, but the same in theory.
It's about half from us. It's about half. I rounded it, to be, not like give off some. Yeah. So you should probably take the number that is published instead of the number that's on the slide. But this is easier to write and digest. So I will tell you that these. I told you, or made you believe that the atoms are very strongly interacting near this Feshbach resonance. And what better way to prove this to you than to take a spin-up cloud, red, and a spin-down cloud, and let them collide with each other at this Feshbach resonance. That is actually a hilarious experiment where you see these two clouds bounce off each other, like two cars in a car crash, or I don't know what other experiment. The scale here is 100 microns. That's the length scale of these images. And this is no simulation, by the way. This is actual data. I was sometimes asked that question, so just make sure. In fact, they bounce off from each other a couple of times, and then it takes over 1 second for them to eventually overlap and diffuse on top of each other. And what's going on here is that the mean free path is as short as can possibly be. It's a very dilute system, 1,000,000 times thinner than air, but the mean free path is as short as it can possibly be, 1 interparticle spacing. And that means it's very difficult for these guys to diffuse into each other. If you think about the average velocity in this Fermi gas, it is actually given by h bar over m times the interparticle spacing. So when you take the product of the average velocity and this mean free path to calculate some diffusion coefficient, v times L, you will always find generically h bar over m to provide you with a scale. We have seen h bar over m a lot in this conference already from the quantum of circulation. Here it shows up as diffusivity of pretty much everything: momentum, spin, thermal diffusivity, what have you. And actually we will discuss in this talk sound diffusivity in these gases. Now you stuff this gas, this mixture of spin up and spin down at low temperatures into your trap. The trap is formed by laser beams. And to make sure that you have a superfluid, you want to rotate that trap and take 2 spoons, again, laser beams that you rotate fast around the cloud. And then in the expansion image, you should see the vortices. I used to say vortices are too small to be seen in situ. That turned out to be wrong. You should come to Richard's talk tomorrow. Little teaser. Now here, let me do this with PowerPoint spoons. Let them rotate around a couple of times and wait a little bit, and you get a vortex lattice coming out after, on the order of a second of healing. One thing we should probably do in the future is to study that healing process very well, because that contains a lot of information as I'm learning here at this conference. This superfluid is very robust. It works in the regime of small molecules and in the regime where there is no molecular state anymore, where the pairing is purely due to many-body physics. So that's nice. It's a healthy superfluid. In fact, normalized to the Fermi temperature, the critical temperature is on the order of 17%. So it's actually the largest TC normalized by T Fermi that you can find. Okay, and if you could scale it to the density of electrons in a solid, you would have superconductivity far above room temperature or far above the melting temperature of most stuff. So if you find a way, that would be great to do. It was mentioned that we can imbalance, of course, the number of spin up and spin down fermions, and then you see the healthiest superfluid, of course, you have for 50-50 because you need the pairing. And then as you imbalance the numbers, you get a small superfluid core surrounded by a normal shell of normal atoms. And in the very end, you have just a small non-interacting Fermi gas, well, a non-superfluid Fermi gas, still strongly interacting, immersed in a big one. As you can see or guess from these images, these are images taken still in harmonic traps or laser traps. I will tell you in a second that we also have now homogeneous box potentials, which should be very good to study precisely this this transition here between the balanced superfluid and the normal state. This actually works also throughout this crossover here, and there's actually critical imbalance that you have to overcome in order to turn the superfluid into a normal state in these trap systems. And you get this simply from saying, if your difference in chemical potentials between the spin up and spin down is larger than the pairing gap, it's no longer profitable for me to pair up, and I will stay normal. So that gives you a phase transition even at 0 temperature from the superfluid to the normal state. We were thinking what would give us a good access to the actual wave function that governs these Fermi systems. We know Gross-Pidevsky doesn't work. Well, can we learn something about waves that exist in the superfluid? And one wonderful wave that does exist for the Gross-Pidevsky equation is, of course, the solitonic wave, which comes about when you twist the order parameter by 180 degrees on one side of your sample versus the other side. And then you let it go, and a wonderful stable soliton emerges. So this actually we wanted to study in fermions, and there is a richer story than for Gross-Pidevsky's situation, because now you have, at least in a mean field picture, the Bogoliubov-de Gennes equations, which in the limit of very small pairing gap become the Andreev equation, which is basically just a Dirac equation, where the pairing gap plays the role of the mass of the particles. And it's a pretty hilarious setup where you have an order parameter that changes sign. If you think of it as a mass, that would mean that the mass would have to change sign, which is bizarre, but people actually thought about this in high energy physics, Roman Jakiev and Rebbe in 1976, and realized, well, in such a scenario for the Dirac equation, there must be a bound state sitting there, which we in the condensation context call Andreev bound state. It's actually the first example of a fractionalized charge, because if you calculate how much atoms sit in this bound state, it's actually 1/2 of a fermion. Now, so that's more like for a motivation. I'm not claiming, unfortunately, I cannot tell you that we found these states yet. That is actually something that we want to do eventually, but it tells you that these solitons will be richer than the Gross-Pideski ones. Here I do show Gross-Pideski solitons just to see what other modes we can expect in a 3-dimensional system. You still have a planar soliton in 3 dimensions, but you can also have, of course, a vortex, or you can have what's called a solitonic vortex. Is when you squeeze your system quite a bit, then the boundary conditions of being in this narrow canal give you something like a hybrid between a soliton and the vortex that has been dubbed solitonic vortex. And of course, you can have more complicated stuff like a vortex ring, which in the cross-section would look like 2 dots here, and more bizarre structures like this phi soliton here, for example. All these came out of Gross-Pideski calculations. Now, how to do this? Maybe that's interesting. You have seen the how to calculate things properly this morning, but how do we actually create these solitons? Well, we just take, it's as simple as that, a laser beam, could actually be a laser pointer to be honest, and mask off half of it so that the atom cloud only sees half of this laser beam. In other words, only half of the atom cloud is exposed to that laser light, and ideally you want a sharp edge. And now why do you do that? Because as long as you imprint this laser light, the phase on that side wraps around faster than on the other side that doesn't have this laser beam acting on it. And you just wait for the correct amount of time to have imprinted a pi phase shift in your superfluid. Then you let it go and hope for the best that you have created something interesting. And this is what happens right after this phase imprint. So we imprint and wait and watch what's going on. When you saw it first, there was some shock wave coming out, emanating from this region where you have imprinted the phase shift. But then there was also this extra stuff in the middle. That is precisely the soliton. So here's the shock wave, the 2 shock fronts, which you always get, you know, you're not making a perfect soliton suddenly. You always mess up your system and create a shock wave. But there is this slow object here, which is not moving much. That is actually a soliton.
They are not really shock waves. I mean, shock waves are supersonic.
Okay, so piled up sound waves.
They're always supersonic.
So apparently I have to be careful with my knowledge. You know what I mean when you look at this, right? They do propagate with the speed of sound, and actually which we checked, it's very nice. And they just carry away the mess that you have created by creating this, this thing. Now, can we show that it's actually a planar soliton? Well, yes, we can actually tomographically cut our cloud. We cut it into slices, like on the order of 8 here, and just check whether in every slice of this cloud we see this central stripe. And we do. So it's really a planar system. I should say, by the way, these are all different clouds. All these clouds come from a new repetition of the experiment. It's not the same cloud, unfortunately. The moment we expose them to light, hell breaks loose. So we have to repeat the experiment, which takes roughly 40 seconds. And then you create hopefully exactly the same kind of situation. And since we imprint it, there's no quantum confusion about where this topological excitation should be. We imprint it, we know where it is. It's in that sense sort of a classical object that we have imprinted into this wave function. And it always shows up at the same spot, of course, where we created it. But then let's evolve time and look at these cross-sections. This soliton does live for a while, but then at some point you see it on top, it seems to break up, and you're left with mostly things that look like 2 dots. This breaking up is precisely the snake instability for solitons. Here it's actually funny, you see like, whoop, how this guy is actually in the process of breaking up. And what you're left with is a situation where you have, very often you see 2 dots, 2 dots, 2 dots in every slice, especially here. Here, however, it's a straight, here it's roughly straight. So if you reconstruct it in your mind, it's actually a ring. So it's a vortex ring. And turns out the evolution at later times is, will make that vortex ring break up, and a single vortex will remain, and that guy will remain for seconds in the system, and we can watch it precess in this elongated cloud. In fact, since it's an ellipsoidal cigar-shaped cloud, it will precess like this along equipotential contours, and we see this. So if you look from top, you see it go back and forth, but we can also, using the tomography, check out in what slice is it, and it goes up and down, so we can reconstruct this equipotential contour. Granted, it's the error bars are there. It would be nicer to have a movie, but this is as good as it gets for now in this type of setup. Gabriele has a wonderful technique to actually take movies of his Bose-Einstein condensates, and you'll see he has wonderful ways to image this. So you might not be surprised, especially after Tapio's talk and many others on this precession, that the vortex is precessing. Let me just tell you, there's no box here, there's no sharp edge. This is a harmonic trap in this experiment. So the reason that they move around is basically the local gradient in the energy of the system. So the Magnus force is provided by the gradient in the energy of the system where you sit. And well, you know this from calculating the energy of the vortex. That would know about the local background density. If you now ask about the force that's acting on this guy, it's going to be the gradient of the density that comes in. Therefore, the compressibility of the soup comes in. And from that, you can easily derive then how the velocity depends on where the vortex is transversely. So if it's in the very center, it's not going to move. But if it's transversely a little bit up, it'll move fast. If it's down, it'll move fast the other way. Yeah. And that gives us a period for which you only need to know where the vortex is, and the chemical potential at that location that decides the period of the vortex. And turns out by equating, by saying, well, this vortex is sort of a classical object that has some effective inertial mass, I can ask, what is that inertial mass? Since the vortex has to move around, when the vortex moves, it has to drag around the entire fluid of the system around it in a large area. The effective mass is actually very large compared to the particle mass, right? So 250 or so is not an unusual effective mass of this vortex that you get. We checked whether now by tuning the interaction strength in this Feshbach resonance business, whether this period formula that I had up there works in the entire regime. So in the BEC limit, we have tightly bound molecules, and it's Grostylewski-like, the whole story. Do we find the correct period as a function of this local chemical potential? Yes, we do. And the formula, which was derived for BECs, that is shown as the solid line is here written down here. In the resonant and unitary case, these are the data in that regime, and there you would take this sort of formula, which is looks almost the same. It's just like a slightly different prefactor from the different compressibility in this regime, and there's some uncertainty on what you should put under the logarithm as the size of the vortex, but these are questions of factor of 2 under the logarithm, so that gives you some error bound here. So it works, the vortex behaves as it should, which is good in the entire regime, BEC, BCS. So now we are in search of a very interesting state, which has to do with the stability of solitons that we discussed this morning. If you fill such a soliton with spin-up atoms that do not find the spin-down partner to pair with, it should actually become stable. And this soliton should not break up. And that is connected to the old story of the Fulde-Ferrel-Lakinov-Chinnikov state, or Loft state, depending on where you are. And in fact, especially the Larkinov-Chinnikov state makes a direct contact to solitons because it's an oscillatory order parameter in your superfluid where the imbalance sits at the nodes. So now, how many nodes do I need? Well, that depends on the imbalance. If I have very few atoms, excess atoms, I need few nodes, and you can, in your mind, just go to a system where you just need one node to stuff in all your imbalance. Oh, that's a soliton. So the LO state directly connects to the soliton, and that's supposedly the ground state. What's the catch? The catch is that the FFLO state occupies a very narrow regime in the phase diagram when you plot the polarization versus the interaction strength. And so that's not good. In our harmonic trap, we scan through many different densities. And so we should actually build a box. And that's what we did. A box allows you to tune your density imbalance and hopefully go to exactly the point in the phase diagram where you want, and then hopefully realize this state. So there are a couple of boxes around, started by this guy, Zoran Hadžibabić, and these boxes turn out to be great for transport measurements, measuring correlations, critical phenomena, and hopefully new phases. So we have this box for fermions, made by a round ring of light that we send to our atoms. And the atoms spend most of the time in the dark. Only when they hit the edge, when they hit the lightning, they're repelled again. So it's really as simple as I'm saying it. It's really a literal box. And to provide the end caps, we have here these sheets of light that make sure the atoms don't go anywhere. Good. So when you have a box, you want to make sure that you do measure for non-directing fermions the Fermi-Dirac distribution. That's what we actually find. You see the Pauli blocking at 1 fermion per momentum space cell and the formation of a Fermi surface. It's maybe not the sharpest Fermi surface you have in mind, but it's difficult actually to cool a non-interacting Fermi gas, as you can imagine. So this is actually not so easy to be in this limit where they don't interact very much. Good. So these guys are happy because it was their 90th anniversary when we did this experiment, and they celebrated, I guess. So now in this box, it's a lot of fun to do transport measurements that in helium were done, for 80 years, second sound, all these beautiful measurements. They were not really directly accessible, only with some tricks in cold atoms, because you didn't have a box, you had a harmonic trap. And the first mode that you see in the harmonic trap system is the center of mass sloshing mode. Well, that's not so interesting because it's completely irrelevant what your many-body interactions are. So the first mode in your system is boring. And then you have to go to higher modes and it's complicated, there's stamping from hell. So you get a complicated spectrum. So let's go into a box. Then we measure transport coefficients, and those are the hardest to calculate. For example, it's the easiest to measure some conductivity on some interesting material. Just put your leads there. But to calculate conductivities is a nightmare. With strong interactions, you don't have a Boltzmann equation because you don't have quasiparticles. You have, for fermions, the sign problem, so Monte Carlo phase, etc. So we like to use our atoms to shed light on this situation. This slide is a little bit not super easy to digest. This is radio frequency spectrum. So for helium-3 researchers, this is just like doing your NMR spectrum. And the width of these spectra actually tells you whether they are well-defined or ill-defined quasiparticles. At low temperatures, you have very well-defined quasiparticles in this system. This is the polaron that also was mentioned at some point. But at higher temperatures, this polaron broadens into this very broad feature, which can no longer be called the quasiparticle. So in this situation, we don't have well-defined quasiparticles. And this is shown here. The width here of these RF spectra can be interpreted as the decay rate of your quasiparticles, and it goes through the roof to a rate given by the Fermi energy, so as fast as it can possibly be, and then eventually it decays slowly at high temperatures once you go back to the actual particles that make your system, lithium-6. So now, of course, there have been lots of studies in these harmonic traps on Fermi gases, but there are all kinds of issues. As you can imagine, if you have an inhomogeneous density, then you're scanning through many different, maybe even phases of matter. Hydrodynamics might not be valid all the way to the edge of your harmonic trap system, etc. So let's do it in a box. Very simple. We have this box. First thing a physicist does with a box of, with a soup of new stuff, you wiggle the box, right? You shake the walls of your box. And what we do is very simple. We just modulate the intensity of one of the light sheets, up and down, up and down. That gives you oscillatory force on the particles and should inject a nice sound wave. And as you do this, well, that's the outcome. It doesn't look very spectacular, but if you take the difference between the shaken and the unshaken box, you see actually the sound wave that you have made. And when I say see, it's really just taking an absorption picture of your gas. Then you see this textbook sinusoidal variation of your density profile, and you already see, aha, it's decaying in space. So there must be something sucking energy out of the sound wave, viscosity or thermal conductivity. And that's precisely what we can get access to now. First things first, we should make sure that we do have a linear dispersion. So I shake at different frequencies and I just watch what my K vector is of the created sound wave. And it is very linear in the regime that we have, we can probe up to 15% of the Fermi momentum. Sorry?
What temperature?
What temperature? Temperature will come in a second because that's a beautiful story. You ask, what's the speed of sound here? Well, it'll have a beautiful relation which tells you that actually Einstein was wrong. So this is E equals 9/10 mc squared. How did Einstein get that wrong? That is really strange. We have now T-shirts that bring out this message in the right way. So what happens here is, in the scale invariant gas, m times the speed of sound squared, not the speed of light, equals, of course, the change in pressure with density at constant entropy for isotropic sound. But the pressure is a universal function of that entropy density times the pressure of a non-reacting Fermi gas. Since we keep entropy fixed, we can take that complicated function out. And so the change in pressure is just like the change of a non-reacting gas pressure with density. And so we get the 5/3 in front. And then you can also know that the pressure is equal 2/3 times the energy density for our scale invariant gas. And you get 10/9 of the energy per particle. So Einstein was not wrong, but it's a fun thing to say. E is 9/10 mc squared, and it works out. You plot the energy, which we can measure by just releasing the cloud, versus m times the speed of sound squared. It's a line. And here you don't see at what temperature I did this. It turns out these lower points were done in the superfluid, and these are actually in the normal state. They're all on the same line, and you don't notice whether you become superfluid or not. Let's explore it a bit more. Let's make some resonant modes. It's another physicist's dream, or if you're in your bathroom and you want to sing, you find the resonances. Did you do this? This is a lot of fun. You find the resonances of your bathroom. Ideally, it's a box. And you find, indeed, that there are standing waves that appear, as you expect from undergraduate or high school, I guess, physics. Let's start again here. The first one would be the sloshing mode, sloshing back and forth. Then this is already the first symmetric mode. And another symmetric mode, because I'm actually shaking both walls, I'm getting the symmetric ones, and so on. So it's like you expect it to be. And we can now take these images, integrate over the boring direction, get a slice like this with high signal to noise, and then produce that slice for each frequency. And then you see in one image the so-called sonogram, or call it the sonogram of the Fermi superfluid. So you see the sloshing mode, blue here, red here, so that's just this mode. And you see the first symmetric mode, the second symmetric mode, there's a little bit of the second odd mode, and so on in basically one picture. What you also see is that initially the modes are sharp at low frequencies, and at higher frequencies they become diffuse, broadened. This begs taking a spatial Fourier transform so that you also associate the wave vector of each mode at each frequency, and you get the linear behavior that we saw before. But now you can also see basically by eye what the width is of each sound mode. And if you have very good eyes, you see also a second harmonic mode popping up in the superfluid. So now we have to put some understanding as to what we see. We just take hydrodynamic equations, but apply them at unitarity. We have the continuity equation. We have Euler's equation with viscosity. And there's only shear viscosity here because this is a scale invariant system. So it doesn't generate any entropy if I compress or dilate the system with the same factor in all directions of space. So there is no bulk viscosity, which is beautiful. The heat is transported and damped by thermal conduction. And of course, the sound wave couples through the density, it couples to temperature, and therefore there's another channel in which it can lose energy. So the sound diffusivity is a combination, the sum of viscous diffusion and thermal diffusion. And for the unitary gas, you can actually work out the prefactors. They only depend on the equation of state, the temperature and the pressure.
So why do you call it the Euler equation since you have the viscous?
So just give your favorite name for it.
Navier-Stokes.
Well, it's easier than the Navier-Stokes because it's 1D for starters. So now, the dispersion relation, once you have such a diffusive term, it actually looks almost linear, but you see there is a damping, which goes like D, the diffusivity, times K squared. K squared can be easily explained. If you have viscous forces, they know about the gradient of the velocity field. But if you have the same gradient over here and over here, you are not feeling a force. You need a curvature of the velocity field in order to feel a force that pushes you one way or the other. So generically in hydrodynamics, you will get a K squared behavior of the damping rate. We should check that. Let's plot the phonon modes here as a function of frequency. And for each mode, we're just checking what's the full width half maximum of these modes. In fact, this is actually a direct measurement of the density response function of the fluid. The width does go quadratically with the frequency and wave number. And from that, you get diffusivity. And, you know, suddenly h bar over m pops up just because that's how the units work out. We observe a certain damping, you know, tens of milliseconds for the 1 over e time at a certain frequency, which was a frequency that I can sing, right? 200 hertz, 400 hertz, I can sing that. I won't right now, but I can. And that gives you a diffusivity that suddenly knows about h bar over m. And it's, in this particular case, at this temperature, 2 times h bar over m. Now it's time maybe to connect to helium. What about viscosity of helium-4? We're talking about bulk viscosity here. So it's not like the story where viscosity goes to 0 at Tc. That happens in narrow capillaries. We're talking about the viscosity of the bulk fluid. And that is totally not 0. At Tc, it actually just drops a little bit by a factor of 2 from Tc to this minimum value here. And then actually grows due to phonon damping at low temperatures. What's that value here? 10 to minus 8 meters squared per second. That's not a number I understand. H bar over m is what I understand. So the diffusivity of helium-4 is h bar over m in terms of its scale. Now we go to helium-3. And we have already heard the viscosity of helium-3 is gigantic compared to helium-4. It starts out down here at a value which is, well, roughly h bar over m. But then it grows like 1 over t squared. It's the world's best Fermi liquid, and so it behaves like it should, 1 over t squared, and it goes here to values of on the order of 1,000 h bar over m. And what happens at Tc? Well, it does drop, but it only drops to this value of on the order of 1,000 h bar over m. So it's still very viscous, even though it's a superfluid. So what is going on? Well, viscosity is always given by the density of the stuff that's moving, the normal fluid, times how long these quasiparticles run around. So the normal fluid density decreases with temperature, but the quasiparticle lifetime increases as you lower your temperature. And so the two factors, actually exponentially large factors, they cancel out. And you're left with a constant kinematic viscosity, which is just given by how much is your Fermi surface still smeared out at 0 temperature. Well, that's the pairing gap. So you get the same formula that you have for a thermal Fermi gas, 1 over T squared, but you replace T by delta, and you get 1 over delta squared. That's what gives you 1000 in helium-3. So what is it for us? Are we like fermions? Are we like bosons in our unitary Fermi gas? This is what we measure, diffusivity versus temperature. We seem to look like bosons in the sense of the scale. We go down to on the order of 1 h bar over m. At high temperatures, we find, yes, it increases as it should in the classical regime, where you have a classical gas of particles, however, scattering with a unitarity limited scattering cross-section. That gives you this T to the 3 house behavior. Down here, you might ask, what's going on at the superfluid transition? We can measure when we enter the superfluid by measuring condensation in the gas, and that happens around 0.17. That's when our condensates start growing out of nothing to something. So we know here we're superfluid, here we're not. The sound diffusivity pretty much doesn't know about this at all. Yeah, so it's very smooth across TC. That reminds us actually of helium-4, where something happens, but it's not very dramatic. Now, what is dramatic in a superfluid? Well, we should retrieve a 2-fluid hydrodynamics model. We should have second sound below TC. So that's taking our Newton's equation, the entropy equation, and adding the superfluid flow. And as we learn precisely at this conference, when there are no vortices, when there's no vortex tangle or something, there is no mutual friction between the superfluid and the normal gas. So I can set a 0 here. And then you see I only have 2 damping constants still, kappa and eta, and there are none of these other bulk viscosities, these zeta 1, 2, 3, 4 that you know from helium-4, they're all 0 thanks to scale invariance. So that's nice. To remind those of you who have were not from the helium field, of course, the story is a very famous, beautiful story. Liquid helium-4 has these 2 sound modes. First sound does this across TC. Nothing special happens. That reminds us of our fluid. Okay, this is actually TC is here, but like nothing so special happens. If you zoom in, you do see something, but let me not worry about that right now. And then second sound is a mode that grows at TC from 0. It's simply the thermal diffusion that you have in a normal fluid becomes a propagating mode below TC. Now, how can we measure that? With the tools that we have. Well, we have in our gas quite a strong coupling between density and temperature. So we can take a potential and wiggle it slightly in an oscillatory fashion on top of this box potential. So we just apply a gradient, which would normally just make the density slosh around. But we hope, thanks to coupling between density and temperature, it should also excite the second sound mode. And if I'm resonant with the second sound mode, that's the one that should win out, and I should not see first sound only, but also second sound. So let's try this. This is our density mode measurement. We create, of course, a gigantic first sound response at 80 Hertz in this example. And we see something that, maybe not, on this projector, you can barely see that there is a response. Turns out we know it's a real response, but you don't know that yet. You're probably not convinced by that data. So what we need is actually a local thermometer. We can see it in the density because density and temperature are coupled, but it's very weak. In fact, the ratio of the heights of these two modes goes with the specific heat, constant pressure, and constant volume, that sort of story. And it's a weak coupling. So we need a local thermometer. And there comes this tool, again, it's like NMR for helium-3. For us, it's radio frequency spectroscopy, where at high temperatures, of course, you see just a peak at the non-attracting atomic value that we use to keep our time, basically. It's not cesium, but it's lithium-6. But at low temperatures in this gas, this peak shifts due to interactions, due to attractive interactions. And that shift is now for us a thermometer. We can just take a particular frequency, maybe this intermediate one here, and sit sort of on the flank of the spectrum, and shine in this radio frequency and ask how many atoms have spin flipped. And we take a picture of those guys, and that should be a picture that knows about temperature. If you do that, this peak at low frequencies grows beautifully, and we see a very strong signal of the second mode and not of the first mode. That is the direct observation of second sound using a local thermometer, which is a nice tool to have also for future studies. Just to finish, I'm actually basically done. I want to give you like this slide as a last one, which is work in progress. That's why there are only 4 points. But basically, from the second sound measurement, we can measure the superfluid density, which is not such an easy thing that we can so easily measure in cold atoms. We have the hardest time, putting our torsional pendulum inside, with the many disks. That's not quite an easy experiment. So this is actually a way to measure the superfluid density. It was measured in a quasi-1D geometry by Rudy Grimm's group using our equation of state as an input. This one does not actually need any external input. It's just from our box, basically. I think the error bars will not be much larger than the size of the points here. So as an outlook, we can now also look at damping of second sound. Here's the damping of such a second sound mode using our local thermometer. And the damping of first and second sound gives us two things that we can measure. And we have two unknowns, the viscosity and the thermal conductivity. So great, we can actually solve and find viscosity and thermal conductivity separately without any unknowns. So that's a wonderful outlook to have. To conclude, what you should take away from this talk, bunch of things, I guess, I don't know, but maybe a unifying theme for strongly interacting Fermi systems that connects us also to condensator systems is we basically don't have good quasi-particles in a large range of parameters. Maybe in the superfluid we do, yeah, but like at near the temperatures that are on the order of the Fermi temperature, we don't have them, and the system usually generically gives you diffusivities which are going like h bar over m. So it's good, you don't have to learn anything new. It's just like economics of circulation playing the role of diffusivities. We have some novel techniques that will be helpful in the future. The box potentials, we can do tomography of these defects and directly visualize heat transport. We're quite excited about that because let's now do this maybe with a bunch of vortices inside and see what we see, for example. So I think all this sets us up for a good future study of quantum turbulence, which we see here and there. When we stir up our vortices, it looks like a mess, but it's so far an uncharacterized mess. And so we have to get serious about quantum turbulence. Thanks for your attention. I should show these guys, and these guys. Sorry. Yeah. Thanks for your attention.
Questions? Go ahead.
So you talked about this soliton which decayed into a vortex which then precessed. But you're doing this you're recreating it every time. So somehow the soliton actually decays like with exactly the same phase?
Yes, so that's something funny, which was actually analyzed by the organizers and our. So what happens usually if you create a perfect soliton, which is just totally planar in your soup, it could one day snake to the left or snake to the right, and every shot we should actually see, either it goes this way or that way. The remnants we will still see, and their position will be pretty well determined, but it could go either way. Turns out we probably have a slight slant in our knife, the knife that we use to cast a shadow on the cloud, and the direction of the laser light that we use to cast this light field, it might have a slide angle to it, and that makes everything go one way instead of the other in every shot of the experiment. So that's one hilarious thing. There's a second thing that breaks symmetries, and that's gravity. So we have a little bit of a sag of the atoms in this harmonic potential, which also tells the soliton where to break up each time. So otherwise you have this beautiful planar soliton. It could break up anywhere, right? But like given gravity, the sag, as was analyzed by Michael and Aurel and Gabriel, you actually get deterministic evolution of this soliton. And if you just touch it and hopefully no one turns any knobs on the experiment, it will every shot decay in roughly the same way. And you can take these movies, even though every frame is a new cloud.
Any other question? Go ahead.
Yeah, also concerning the decay of the soliton, then it decays in the vortex ring, and then you show that it decays in the vortex line. So, but actually, you should expect that it decays in two vortex lines. Is it because it's off center, so you don't see one because it's expelled, or?
So this was analyzed also by you partially, but also.
So the
others.
question is that the soliton starts just for.
Yeah, sure.
It starts as this goes into a vortex ring, and then why doesn't it decay into two lines instead of one line?
Yeah, so beautiful question. This is something we have the hardest time really understanding. What is the case that, you know, for the parameters that we use, we always end up with a single guy and not two, and that one stays around for a long time. So now you have to look at simulations to understand a little bit what actually happens in this complicated breakup. Turns out this vortex ring, when it usually should be a beautifully stable object, but when it touches the edge of your superfluid, it is no longer stable. So it breaks up into, well, it could either be a single vortex line, or it could break up at two ends and then give you two vortex lines, a vortex anti-vortex pair. And then usually would say, oh, why don't they happily go together through the soup in some way? Usually there's what some people call the slingshot event, that one vortex wraps around the other and flies out to like infinity basically, and leaving one behind. So this was actually seen in simulations of the Gross-Pideski equation, for example, and also the effective field theory that you did. So it's pretty hilarious. So.
Yeah, just quick. But also when you calculate the precession, right?
Yeah.
There was you cited different articles, also one by Lund and Au, and they used to coming back to the question I was asked before, the image vortices to calculate the precession.
Yes.
So I mean, just want to say, what's your opinion on so what drives a vortex in a harmonic trap? That's degrading the curvature of the vortex or the image.
I can give you the answer. Oh, God, sorry.
So the question is, what drives the precession of this vortex around the trap? Because it's a harmonic trap, there's no image vortex in particular.
There's the discussion on that.
Yes. Okay. You need to share your screen again if you want.
Oh, sorry. Okay, so what happened?
Zoom.
So this is a beautiful question, and now I can tell you how I would have answered it before last Friday, and I will answer it also after Friday. So before last Friday, I would have said what I said, like in a harmonic trap, it's driven by the local force acting on the vortex because the density profile is not flat, but it has a gradient. So great, so that gives you a force and it goes. Whereas in a box with sharp walls, you don't have a density gradient, but you have the image vortex. So that would have been my simple story. But Friday, Tapio visited MIT, Tapio Simula, and actually, sorry, I'm looking to the wrong person there. Tapio visited MIT, not that I don't want to look at you, but he visited MIT, and he showed the simulations of this harmonically trapped gas, where he showed, in fact, it's even in the harmonic trap, there are two contributions, apparently. One is from the density gradient that acts on you, and one is from the phase profile of the superfluid, which basically you could write down in probably some terribly complicated way as image vortices far outside your condensate. So it's the two, I fear, and it's not a simple answer.
So Fett in his paper in 2001 was wrong.
Yeah. So Fetter's formula is actually the dashed line.
Yeah, but he was saying that because the density vanishes, there's no you don't have to put the image vortex because
So it turns out, I don't know whether that's the reason, but the dashed line is Vetter and the blue line is Lund and Au.
Is that the reason?
The value, the actual value is quantitatively very, very, very close.
So it's more.
Okay, any other question? One last question. Go ahead, listening.
It's a comment concerning the low phase.
Yeah.
So you showed the diagram due to radicality and the sheeting. Where it showed the low phase, it's only in the BC side, a very narrow window.
Yeah.
But actually, Michael and I performed an analysis of the Unitarity. They find an extremely wide window there.
Yeah, so I show this slide so that no one else tries this.
No one.
I'm just kidding.
No, I didn't understand what you said.
So that no one else tries.
It's very difficult.
It was based this year on a really very careful analysis of the equation of state and quantum Monte Carlo simulation and experiment and so on. I think it's worth looking for that data.
I'm with you. I totally believe it should be a generic thing, and it starts with the soliton stability. That's maybe the first thing to show, and then I'm sure it extends to soliton trains and stuff. Well, sure, it's a bit too strong word, but in that sense, I fully agree. This red sliver here is putting in two very particular, a particular trial wave function, which is really the Loff trial wave function. That particular solution has a narrow sliver of existence, but there's the entire range down here, which already has a soliton in there, two solitons, and
but the
some
gap
other
is
stuff.
very small. It would be hard to see.
Yes,
And the
so
other,
it's still hard.
the other potential problem is it might be a real crystal.
Exactly,
So
we
you
don't
need
know.
your-
I guess we don't know whether it will be a stable soliton train in a 3D system.
Well, that depends on the size of the trap.
Hmm.
Depends on, and actually there are some results from Piotr and Gabriel now. You see where they looked at spin imbalance droplets, which I believe is a manifestation of the same thing. You see, you create an imbalance in a spherical drop, and then you see that the change in phase exactly like in the log phase. You see from minus side to plus side outside, they are very stable, and that could be in 3D. You see, and they'll be very stable because what the sphere will go away.
Mm-hmm.
See, for this you might have the snake instability, but for the sphere probably you won't.
It'll be intriguing to study.
Yeah.
Definitely.
All right.
You do one?
Okay, last talk.
I also have a very quick comment. Yesterday there was a remark that the equations that have been engraved into the walls of the neighboring buildings should have corrections to them. I encourage you to go and chisel in the 9/10ths.
Yeah,
Very
no, I totally do that.
easy square.
Totally do that.
Do it late at night though,
Okay,
and not on
okay.
the recording.
All right, let's thank the speaker again.
Thank you. How do I go?